looking at the region above which we're integrating. So as you saw, I'm dividing this interval from A to B lies on the x-axis, and the interval C to D lies on the y-axis, so CD and AB, okay? So here I have this rectangular region right here, right? This rectangular region above which I'm integrating, right? Or in other words, I'm looking for the volume under this surface S, right? Above this rectangular region. Okay, so the question is how, in calculus, right? The question is how am I going to approximate this? What is one tangible thing that I can grasp onto so that I can extrapolate from there? I can find the expression for n terms, and once I do that, I can take the limit as n goes to infinity. As a matter of fact, here we're going to see that it's going to be slightly different. It's not going to be only n terms, but also it's going to be well, you'll see. Okay, so let's divide the interval a b into n subintervals. Okay, into n subintervals. That gives us this, and so on and so on. Okay, so basically I have that a is equal to x naught, okay, less than x1. So a is x naught, this is x1, less than x2, less than xm, which is equal to b. So I've divided the interval ab into m subintervals. On the other hand, I divide the interval cd into n subintervals. So 1, 2, 3, 4, and all the way up to n. So this is what we get. Okay, this is what we get. So y1 less than y2 less than less than yn, which is equal to d. Okay, so d is equal to yn, and this is y naught, and b is equal to xm, and a is equal to x naught. Okay, so what do we have here? We have something that is going to be very complicated for me to sketch, but it's going to be much easier if I just show you this graph right here. Okay, so here it is. If I'm looking for the double integral, sorry, for the volume below this surface, right, on the rectangular region defined for x from -2 to 2 and for y from -2 to 2, right, this is what I have. Okay, okay, so if I divide, where is x? It's right here, positive and positive, right? So here I can increase the subintervals, right? So here, for example, it's 3 by 3, okay? Or 4 by 4, or 5 by 5, and so on and so on. So what happens? I'm getting, if I look from here, I'm observing I get a mesh, right? So I have 1, 2, 3, 4, 5 subintervals, and 1, 2, 3, 4, 5 subintervals. This was graphed in such a way that the subintervals that I get on the x and the y axis are the same, which is fine. It doesn't have to be like that, but it's fine, okay? And then this is what we get, okay? We obtain a mesh. How this mesh will help us in evaluating the volume under this surface. Okay, so look at this. Let's take this sorry. Oh, yeah, 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 yeah. Sorry about that. Give me a second. Give me a sec. All right. Sorry about that. Slightly lost here. Okay, so we're back here. Okay, above this small rectangle, right, I create a box, okay? And the question is, can I evaluate the volume of this box? Well, if I choose a particular point, and in this case is given this, this point, right, for each rectangle. If I choose a point, okay, then what do I have? I have the width and the length of the box, and I can calculate it. Why? Because I have divided the interval AB onto n subintervals, so that's fine, right? And I've divided the CB interval on the y-axis on m subintervals, right? So that's very simple to find the length and the width of the box here in the xy, not the box, sorry, of the rectangle in the xy plane. And then how I'm going to evaluate the volume of this box? Well, if I choose some particular point on this rectangle, given the function z is equal to f of x, y, I can simply evaluate the height of the box by evaluating the function at that particular point, right? So this is going to be the first box, and then if I change it here, it shows you how you go from box to box. Every particular box. If we see all the boxes, there you go. This is how we approximate the volume. Excuse me. This is how we approximate the volume under the sphere. So what does that mean? That means that the volume under the surface, not the sphere, sorry, the volume under the surface is going to be approximately equal to the sum of a function evaluated in each rectangle, f of ij, y of ij, and now this is delta aij. Okay, so first let us discuss what are these, okay? Delta aij is equal to, this is times, right? Sorry. Delta aij is equal to delta xi times delta yj, okay? Where delta xi is equal to xi minus 1, and delta yj is equal to xj minus 1, okay? So that is nothing else but, right, the width and the length of each of these sub-rectangles of the rectangular region above which I'm integrating. Okay, those are xi and xj, xi and nyj. Okay, so that means that knowing those two, I can find the area of each of these sub-rectangles. Okay, now as I said, choose any point xij, yij in each particular rectangle, okay? And because we have to agree on what point are we gonna take in each box, we put this star, okay? Then what do you have? You have the height of each box times the area of each box. This gives you the volume. This gives you the volume. This gives you the volume of each. This gives you the volume of each box. Okay. Okay. But now look at this. This is something. This is the most important part that will actually lead us to. That will actually lead us to the double integrals. First, here I have to sum them up for each j, right? So remember that we divided the y interval into n subintervals, right? So first of all, I have to add them up all the way from C to D, right? So that's why here it says sum all the terms from 1 to n. But then we have to sum them up for each of the subintervals along the x-axis. So that means sum them up when I goes from 1 to n. Okay? And then when this volume is going to be exactly, when can we find the exact value of this volume? When I'm going to find the limit as this is m. As n goes to infinity and as m goes to infinity of this double Riemann sum but there is nothing else. The definition of the double integral. So the definition of the double integral over a rectangular region R of a function defined in two variables, dA, okay, is equal to the limit of the double Riemann sum f of xij star yij star delta aij when j goes from 1 to n and I goes from 1 to m, okay? And when the length of the partition goes to 0, or simply when n and m go to infinity. So this is the definition of the double integral. Okay? So let us see another graph like this. A second here. Okay, what do you guys see? Nothing. Okay. So what is going on here? Sorry, guys. Okay, so I have this surface here, and I can change the value of here. I can change this subintervals along the x and the y-axis. Okay, and as you can see, as I increase the value of these subintervals, okay, you can see that the sum of the volumes of these boxes is approximating, is coming closer and closer to the actual volume under the surface. Okay, so this happens for 17 by 17, and so on and so on. Okay. So evaluating the double integral in this case, as you might imagine, is going to be very, very difficult. So let's talk about iterated integrals. And iterated integrals are nothing else but basically they tell us how to evaluate these double integrals. Okay. Sorry. So for example, we have to evaluate the double integral of 4 minus 2y, okay, dA, where a is bounded by, so x is between 0 and 1, and y is between 0 and 1. Okay? So basically in the xy plane, we're talking about this rectangular region, 1 and 1. And this is just going to be a plane, so we don't really have to use double integrals, but nevertheless, let's evaluate this. So here you will choose how are you going to integrate this, right? So obviously x goes from 0 to 1, so x goes from 0 to 1. If you write here the limit of integration in terms of x, first you have to integrate in terms of x. And then in the second one, if you write the limit of integration in terms of y, you have to write here dy. So the outer integral sign goes with the outer differential, and the inner integral sign goes with the inner differential. Okay? How do you evaluate this? Similarly, like partial derivatives, when you evaluate the integral with respect to x, everything else you treat in terms of you treat as a constant. So you can see here 4 minus 2y, x doesn't play any role in this expression, so I treat the whole expression as a constant. An integral of a constant times f of x is just c times the integral of f of x, right? And the integral of constant times dx by this logic right here is equal to c times x, right? So I treat 4 minus 2y as a constant. That's going to be 4 minus 2y times x evaluated from 0 to 1 dy. That will give me the integral from 0 to 1, 4 minus 2y times 1, right? X, when x is 1 is 1, minus 0, 1 minus 0 is 1, times 1 is 1 dy, and then you have a single integral in terms of y, so that's 4y minus 2y squared over 2, evaluated from 0 to 1. That's 4 minus 1 minus 0, when you plug 0 for both of them, and that integral is equal to 3. So what would be the geometrical interpretation of this iterated integral? Okay, remember that what we learned in Cal 2, right? So when we learned the surface volumes of solids obtained by rotation, so you had something like this, let's say, and you rotate this around the x-axis, you get this, right? So how much is the volume of this? How much is the volume of this solid? Well, you slice this somewhere, anywhere, right? Figure out what is the intersection between a plane and this solid, and that's going to be in our case a disk, right? Evaluate the area of the disk, and the volume of the whole solid is the integral from A to B, the area of the slice dx, right? We learned this in Cal 2, right? But something similar happens with these iterated integrals. Why? Because if you have an integral here, let's say from a, b, dx, f of x, y, sorry, dy, and here you have cd to stay in accordance to our first sketch, right? What did we say? When I evaluate the first integral, right, I treat every expression, I treat every term that defined in y as a constant, okay? So if you have a surface and you start treating every y as a constant, what do you get? You get slices of the surface, right, with a plane parallel to the yz plane. Okay? Or in other words, let's say that I'm using double integrals to evaluate the volume under this surface, right? So first, if you write that this is, first I'm going to integrate with respect to x, and then with respect to y, that means that first I'm taking y as a constant, right? If I take y as a constant, for each constant y, I get a plane parallel to the xz plane, right? So for each of them, what do I get? I get nothing else but one-dimensional area under the curve on the interval defined in terms of x, right? Okay. And then if I evaluate in terms of y, basically I'm just summing up all of those areas. So again, if I evaluate first in terms of x and then in terms of y, right? I take that at the beginning, y to be a constant. If you take y to be a constant, that means that I'm intersecting the surface with a plane parallel to the xz plane. That will give me basically an area, sorry, like this, an area under a curve. And for something like that, what do? We just evaluate using Cal 1. So that's how we evaluated the first integral, just with techniques learned, sorry, in Cal 2, learned in Cal 2, right? And then with the second integral, I basically summed all of these areas up along the y-axis. And that's how I get the volume. That's exactly what we did when we evaluated volumes of solids of revolution, right? On the other hand, if I first evaluate the integral in terms of y, then I take x to be a constant. When I take x to be a constant, that means that I'm taking a plane parallel to the yz plane, and by intersecting this plane with the surface, right? In one dimensions, I basically just get the area under a curve. Okay? And in order to get the volume under the surface, now I need to add all of these areas on the interval from A to B. And that's the whole idea of the iterated integrals. Okay? Now we can do a lot of examples here. Are there any questions? So example 2. So evaluate the double integral xy minus 3xy squared dA, where r is equal to the region where x goes from 0 to 2 and y goes from 2 to 1. Okay. So here I'm just going to evaluate first with respect to y, dy, then dx. Y runs from 1 to 2, xy minus 3xy squared. X runs from 0 to 2. This is equal to. So first I evaluate this integral with respect to y. Okay, so from 0 to 2 dx. I treat each x as a constant. Xy squared over 2 minus 3xy cubed over 3. Not to be confused, it's usually easy to write here that y goes from 1 to y goes from to 2. Just to always to recall what integral did you take first. That's equal to, from 0 to 2, let's just simplify this first. So this 3 cancels out. So now plug y is equal to 2, you get x times 4 over 2, y squared is 4, minus x stays as it is. I just plug y is equal to 2, 8x, because 2 cubed is 8, minus, open parenthesis, x over 2, right, because y is 1, y squared is 1, minus x times 1 cubed is just x dx. And this is a very simple integral for you to finish. This is going to be equal to integral from 0 to 2, 2x minus 8x minus plus x over 2 dx, right? So you cancel 4 and 2, you get 2x minus x squared, x over 2 minus x is negative x over 2, with negative is positive x over 2, and that is how much? I don't know. 6 minus 1/2 is 11 over 2. So negative 11 over 2 integral of x from 0 to 2 dx is equal to negative 11 over 2 x squared over 2 evaluated when x goes from 0 to 2. And that's negative 11 over 4 times 4, which is negative 11. Okay? Any questions? One obvious question here that might pop out is, well, how come we're talking about volumes when, how come we're talking about volumes and I get a negative value? Again, this is interpreted as a volume under the surface as long as the surface is above, the xy plane. Okay?
I have a question.
Uh-huh.
Is it like, can you switch the order of dy and like
Very good. Yeah, and that
integral?
is absolutely. Do you hear me?
Okay. Yeah.
Okay. So 6, that's being confirmed by Fubini's theorem that I'm not going to prove here. That the double integral dy dx is equal to the double integral of dx dy. Of course, you have to change now. Y runs from C to D, so C to D, and x runs from A to B, so x runs from A to B. Okay? So that's the Fubini's theorem, and it doesn't matter what order you choose, the result is going to be the same. What matters is what is going to be easier for you to evaluate. Okay? So let's do a few examples. Example 3, the double integral over the region R, x times sine of x plus y dA, where the rectangular region is defined as 0 to pi over 6 and 0 to pi over 3. Okay, how to read this region, right? It's always x times y, right? X times y. So that means that x is between 0 and pi over 6, and y is between 0 and pi over 3. Okay? So nobody is going to actually tell you, do it this way or that way, right? You have to choose the order of, integration, okay? So it's up to you. So let's see, if first I evaluate this in terms of x, well, I'll have to use the product rule, okay? Which is fine. Sorry, not the product rule, the integration by parts, right? Right here, x times sine of x plus something. I have to use integration by parts. So if I first integrate with respect to y, I just have to integrate this function here, and I'm going to treat x as a constant. So because I don't know any better, let's just try it that way. So first integrate with respect to y. Okay, so y runs from 0 to pi over 3. X runs from 0 to pi over 6. X times sine of x plus y. First in terms of y, then in terms of x. Okay? So I treat x as a constant. X times integral of sine is negative cosine of x plus y, right? Evaluated when y goes from 0 to pi over 3, right? dx. That's equal to negative x times cosine of x plus pi over 3 minus cosine of x dx. And now this can be written with this negative coming in here, 0 to pi over 6 can be treated as x cosine of x minus x cosine of x plus pi over 3 dx from 0 to pi over 6. And here you just use integration by parts for both of them, and you can finish this problem. Any questions?
I have a question.
Mm-hmm.
Can we keep so like on the second to last line, like you wrote the integral from 0 to pi over 6,
Yeah.
x times minus cos of x plus y. Can we directly integrate that, like with respect to x, and then like plug in the y's and plug in the x's after?
I wouldn't go that part.
Okay.
You can, but I would never do something like that. So it's up to you. Okay?
Great, thanks.
Let's do another example. Excuse me. So the double integral, as you can see, with this rectangular, when we integrate above rectangular region, they never give us the order of integration. They just give us what R is. So the x interval goes from 0 to 1, and the y interval goes from 0 to ln of 5. Okay, so you can rewrite this right away as x goes from 0 to 1 and y goes from 0 to ln of 5. Okay, now again, it's up to you. If you take integrate first with respect to x, you have to use the integration by parts. Okay, so why don't we can do it that way now. So first integrate with respect to x. Okay, so x runs from 0 to 1, x e to the power xy. Okay, and then dy and y runs from 0 to ln of 5. Okay, so using integration by parts, u is equal to x, du is equal to dx. So I'm just evaluating this integral here. V is equal to r e to the power of x y, sorry, that's dv, and then v is equal to e to the power of xy, and I'm treating y as a constant times 1 over y. Okay, so this is going to be the integral from 0 to ln of 5 x over y e to the power xy, okay, minus the integral of 1 over y e to the power xy dy. So this is going to be evaluated from 0 to 1 in terms of x, 0 to 1, and then the whole thing dy. Okay, this is the integral from 0 to ln of 5, plug 1 for x, right? Sorry, x here. So you get 1 over y e to the power y minus 0, when you plug 0, right? 0 over anything is 0 times anything is 0, minus, now this is a constant here, 1 over y, and then I'm left with the integral of e to the power xy, which was evaluated here. That's e to the power xy times 1 over y. And this is evaluated from 0 to 1. And dy. Okay. This leaves me with from 0 to ln of 5, and these are x's, right? 1 over y e to the power y minus 1 over y squared e to the power y minus e to the power 0 dy. Okay, so that's equal to the integral from 0 to ln of 5, 1 over y e to the power y minus 1 over y squared e to the power y minus 1 over y squared, because e to the power 0 is 1 dy. Okay, which is equal to integral from 0 to ln of 5 y to the power negative 1 e to the power y minus y to the power negative 2 e to the power y minus y to the power negative 2 dy. for each of these, I have to use the integration by parts. U is equal to y to power -1. Du is equal to is this correct? -1 over y squared. dv is equal to e to power y. v is equal to e to power y. And if I take the second one, u is equal to e to power y, du is equal to e to power y, dv is equal to power -2, v is equal to y to power -1 times -1. Right, I'm trying to simplify this somehow. So if I just use, for the second integrand, I use this, I get y to power -1 e to power y minus negative y to power -1 e to power y plus the integral of -1 e to power y dy minus y to power -2 dy. And obviously I'm getting stuck here, and that means that I have absolutely done wrong choice of order of integration. Okay, this was way more complicated, so you can come back here at the beginning, okay, and then change the order of integration. So first now I integrate in terms of y, then in terms of x. If I first integrate in terms of y, this goes from 0 to ln of 5, and then if I integrate in terms of x, from 0 to 1, and I have x e to power x times y. Okay, x and x are constants, so this is 0 to 1. First I integrate with respect to y, and I get x times the integral of e to power xy is e to power xy over the constant, and the constant here is x, right? And I evaluate this when y is from 0 to y being ln of 5 dx. But now these are out, and I just end up with the integral from 0 to 1 e to power x ln of 5 minus e to power 0 dx. But this is nothing else but 0 to 1 e to power x ln of 5 minus 1 dx, right? Which is equal to the integral of 1 is x, the integral of e to power x ln of 5 is e to power x ln of 5 over the constant ln of 5 minus evaluated from 0 to 1. And this is equal to e, when I have 1, right, e to power ln of 5 over ln of 5 minus 1 minus e to power 0 over ln of 5 minus 0. And that's it. Am I back, guys?
Yeah, you're back.
Yep, you're
Good.
back.
E to power ln of 5 is 5, e to power 0 is 1, so you have 5 minus 1, it's 4 over ln of 5 minus 1 is your answer. And here you can see how important the right choice of order of integration is, right? With one of them I got stuck. I had to use multiple times the integration by parts. Here excuse me, here I solved this double integral in 4 lines. Any questions? Well, that's about it with these double integrals. Let's just write down the properties. Properties of double integrals. So you have the double integral over the region R, f of xy plus or minus g of xy dA, that's equal to the sum or the difference of the double integrals over the rectangular region R. Of course, constant double integral over constant times the function fxy dA over the region R is the constant times double integral f of xy dA. Okay, standard standard properties. If R, so this is 1, 2, 3. If R is a union of two regions, okay, where these regions don't intersect, right? S intersection T is an empty set, then you can write this as okay, and for if f of xi can be expressed as a product of two functions solely defined in x and in y, right, if that's possible, okay, then the double integral of the function f of xy dA over the region R can be written as a product g of x dx and h of y dy from a, b, and c, d, okay? But be careful, this rarely happens, okay? So for example, for example, with this last property that we wrote down, this integral xy minus 3xy squared, right, R dA, where R is 0, 1, 0, 2, and y is 1, 2, okay? Now with this last property that I just wrote down, if the function f of xy can be expressed solely as a product of a function in terms of x and a function in terms of y, then the double integral becomes a product of two single integrals. And that's exactly what happens here, because this is equal to x times y minus 3y squared dA over the region R. So this is g of x, and this is h of y. So this can be written as the integral, single integral from 0 to 2, because x goes from 0 to 2 of x dx, and then y minus 3y squared dy, y goes from 1 to 2, from 1 to 2. So you can see that there is a, this is going to be way easier than what we did before with the, so this is going to be x squared over 2 from 0 to 2 times y squared over 2 minus y from 1 to 2. You don't have to treat anything as a constant and so on and so on. So this is just 4 times 4 over 2 minus 2 minus 1/2 minus 1. So this is 4 times
Isn't it y cubed?
Huh?
Isn't it y cubed on the right?
Sorry. So thank you. So this is 4 over 2 is 2, even that mistake, right? 4 over 2 is 2 times 8 over 2, no, 4 over 2 again, sorry, this is squared, minus 8 minus 1/2 minus 1. There was no difference here, okay? So 2 times, this is 6, right? 2 minus 8 is negative 6, and this is negative 1/2, so plus 1/2. That's 2 times negative, I don't know, 11 over 2, right? And we got negative 11. And I don't know if in the previous case we got negative 11 only. Also, can you check this same example previously? How much did we get? Oh, you don't see anything, sorry.
Yeah, we also got minus 11.
Okay, and so that's it about this section. Are there any questions? Any questions, guys? Okay, if there are no questions, then I'm going to continue towards the next section, which is 15.2, double integrals okay, over general regions. Over general regions. So what does that mean? Well, it's absolutely acceptable to ask the question why the region above which we're integrating has to be rectangular. Well, it doesn't have to be rectangular, right? It can be any general region. The idea is, let's say we're integrating over this region right here. The idea is that again, you make this as a mesh of combination of this subintervals in terms of x and y, and then you approximate, right? You approximate the volume under the surface above this region as a sum, right, of the volumes of all the boxes created above these regions. Okay, so the double integral, it's basically the same. Okay, so let us just jump into an example right away and check what will happen. Okay, so evaluate the double integral of f of x y dA, okay, where a is bounded by the x-axis, the line y is equal to x, and x is equal to 1. And f of xy is equal to 3 minus x minus y. Okay? So first of all, let's find the region above which we're integrating. Okay? So it's bounded by the x-axis. The line x is equal to y, and the line x is equal to 1. So I'm integrating above this region. Okay. And the question is, how am I going to set up this double integral? Where does x go from where to where, and y goes from where to where? Okay. Because this is not a rectangular region. One of the bounds is going to be in terms of a variable. So there are two choices, okay? You fix x, the first option. You say x goes from this graph, obviously from 0 to 1. You fix x. And then y, for each x, y goes from 0 to x, right? When these two intersect, this is 1, 1. Option 2 is fix y. Y goes from 0 to 1, but then x, now be careful, x goes from where to where? X goes from here to here. So x is at most 1, and at least it's y. Okay. So those are the two options. And by the Fubini's theorem, I know that whatever option I choose, the answer has to be the same. The question is, what is the easier option? Nobody is going to ask you, choose the easier option, or what is the easier option, okay? But of course, in order to save time, you have to, it's better for you to choose wisely, okay? So this integral here, first I can evaluate 3 minus x minus y. I can first evaluate it in terms of y. Y goes from 0 to x. And then the x goes from 0 to 1. Okay? So integral from 0 to 1, I integrate with respect to y. 3y minus xy minus y squared over 2, where y is 0, and it goes all the way to x. dx. Now let's plug these values for y in here. That's the integral from 0 to 1. When y is x, I get here 3x, minus y is x, I get x squared, minus y is x, I get x squared over 2, minus, when you plug y everywhere here for 0, you get 0, dx. Okay. Let us simplify this expression a little bit. 0 to 1, 3x minus 3x squared over 2 dx. And now you can evaluate how much is this. 3x squared over 2 minus 3 over 2x cubed over 3 from 0 to 1 is equal to 3 over 2 minus 1/2. That's 2 over 2, which is equal to 1. Okay. Now, as an exercise, I will leave you guys to confirm that if you change the order of integration, if you take option 2 now, first you integrate with respect to x, so then with respect to y, x goes from y to 1, from y to 1, and y goes from 0 to 1. And the function is 3 minus x minus y. I'm going to leave you as an exercise to confirm that this is also 1. By the Fubini's theorem, this has to be 1. Okay? But be careful. What is the only thing that you cannot do? You cannot leave as the outer integral. You cannot, for example, write it like this: y to 1, 0 to 1, 3 minus x minus y. The a y dx. This is not admissible. Why? Because at the end of the calculation, you will plug y and you will not get the value of this integral, right? So the only constraint here in terms, it doesn't matter what option you're going to choose. What it matters is if the variable is bounded by another variable, that's always has to be the inner integral. That's the only constraint that you have. Okay? Any questions?
Let's say we want to integrate over like the area of a circle. Since we can't express it as like a function, do we have to like separate it in two? Like you have to put like, let's say y in terms of x and like y equals square root of like x squared, let's say plus 1.
Keep
And
in
then you have to
mind
do like
this.
minus.
Yeah, sure.
Okay.
So keep in mind, give me a second, what? I don't know. Ok. Cadê? Seria já luz, cara. I'm not going to solve this. Let's say that you have xy dA where a is equal to a is the circle x squared plus y squared is equal to 9. Okay, so it's a circle with radius 3, right?
Mm-hmm.
This is nothing else but this semicircle plus this semicircle. So y is equal to square root of 9 minus x squared, and y is equal to negative square root of 9 minus x squared. But now keep in mind this property of the double integral. If the region above which you're integrating can be expressed as a union of two regions where they do not overlap, then you can split your integral into two different integrals, over the region S and over the region T, right? So these two integrals, sorry, these two regions don't overlap. Right? The upper semicircle and the lower semicircle. So this can be expressed as xy dy, let's call this region, not dy, dA, over the region S, plus xy dA over the region T. Okay? Charles, are you satisfied?
Yep, makes sense.
Of course. What makes more sense is the following thing. Right? So from here, I get that r is equal to 3, right?
Mm-hmm.
And theta runs from 0 to 2 pi. So this integral, much easier, can be written as 0 to 2 pi d theta 0 to 3 dr r squared sine theta cosine theta. Way easier, right? Now, because this depends only on in theta and this depends only in r, this integral becomes from 0 to 3 r squared dr times the integral sine theta cosine theta d theta 0 to pi. This is section 15.3, evaluating double integrals in polar coordinates, and maybe that's a little bit too fast to cover that today also, right? So we'll just leave this for Wednesday if you guys don't mind.
Yeah, okay. That's so cool. Oh my God.
Okay, so let's do a few more examples of this type. And okay, so let's this example. Sketch the region of integration. Okay, so you have 4x plus 2 dy dx, where y goes from x squared to 2x and x goes from 0 to 2. Just sketch the region of integration. Okay. So what do we have here? That y is bounded by the graphs of x squared, because this is a lower limit of integration. It's greater than x squared, is less than 2x, and x runs from 0 to 2. Okay. So how much is that going to be? Okay, x is always positive, so I can just concentrate on the first quadrant, right? And I have the graph x squared, and I have the graph of 2x. Let's say this is 2x. And when x is equal to 2, I can see that these two graphs meet right here. So this is the region of integration, right? Y is between x squared greater than x squared. When we talk about y, that means y is to the right of x squared. Sorry, y is above x squared. I'm so sorry. Y is above x squared, okay? And it's below 2x. And it's below 2x, and x goes from 0 to 2. If you want to change the order of integration, now x is going to be greater than the line. The line is expressed as y equal to 2x. In terms of y, that's going to be y over 2, right? And is less, so x runs from y over 2, the line, and it's less than the parabola, which expressed in y is just going to be positive square root of y. And in this case, y is greater or equal to 0, right? And where do they meet? Well, they meet at 4. That's easy to evaluate, right? X squared when x is 2 is 4. So sometimes you're given a question like this, but it's very difficult to evaluate the integral in terms of y. You have to change the order of integration. Of course, first by sketching the situation. So here is going to be 4x plus 2 dx. X is running from y over 2 to square root of y, and y is running from 0 to 4. Any questions? So let's do another example. Change the order of integration. For the integral 1 to e 0 to ln of x, xy dy dx. Okay, so y goes from 0, y is bounded below by 0, above by ln of x is bounded between 1 and e. So let's catch that. This is y is equal to ln of x, okay? X is between 1 and e. Ln of e is 1, and this is just 0, right? So y is greater than 0, less than ln of x. X is between 1 and e. Okay. What does that mean? If I change this in terms of y, now x has to be bounded by the function in terms of x. Now x, so this is the region that we're talking about, right? This is the region above which we're integrating. What does that mean in terms of x? X is greater than this function y is equal to ln of x. How much is that in terms of y? That's e to power y. And it's less than x is equal to e. Then y is going to be bounded by the constants of this region from 0 to 1. So this can be written as the double integral of xy. First integrate with respect to x. That means from e to power y to e. And then with respect to y from 0 to 1. Any questions? Now let us just do an example here to show you how this works in an actual question. Okay, so the last example, evaluate the double integral from 0 to 2 x to 2 y squared sine of xy dy dx. First thing that we want to notice is that this function cannot be expressed as, this integrand cannot be expressed as a product of two functions solely defined, independently defined in terms of x and y, because of this guy right here, sine of xy. Okay, that means I take on the standard procedure. I treat x as a constant and I evaluate the integral with respect to y. In order to do that, I need to figure out, first I need to use the integration by parts. So u is equal to y squared, du is equal to 2y, dv is equal to sine of xy, v is equal to negative cosine of xy over, I'm integrating with respect to y, so x. So this here becomes the integral from 0 to 2, negative y cosine of xy over x, evaluated when y is x and y is 2, plus the integral, this is all inside, plus the integral of 2 y cosine of xy over x dy, and then the whole thing dx. Okay, this becomes extremely ugly because this is going to be the integral from 0 to 2, negative 2 cosine of 2x over x. Again, I have to use the integration by parts when it's going to come, when the time is going to come to find the integral with respect to x. Plus, here I have to use the integration by parts. So here u is equal to y, du is equal to 1, dv is equal to cosine of xy, v is equal to sine of xy over x. So plus 2 over x times y sine of xy over x evaluated when y is x and when y is 2, minus the integral of sine of xy over x dy. And then I have to find another integral right here. And at a certain point, you have to say, okay, this is ridiculous. There is no, okay, enough is enough. Okay, so in that case, you turn the page and you start over, right? Because we don't learn integration by parts in this course, we'll learn double integrals. So let me just again go back and write down the integral 0x to 2 y squared sine of xy dy dx. If I find the integral first with respect to x, maybe some things will change. So I want to change the order of integration here. In order to do that, first I need to sketch the region. Y is greater than x and is less than 2, and x is greater than 0 and it's less than 2, right? So let's see how that looks. X, y, and y is equal to x. So y is greater than x and it's less than 2. This is 2. And this is 2. So y is greater than x and it's less than 2. And x is between 0 and 2. So this is the region that we're talking about. Okay. Now let's rewrite this in terms of where x is going to be bounded by some function. So x is from 0 to this line. That line is going to be, in terms of y, is just y, so from 0 to y. And y now is from 0 bounded by 0 and 2. So I can rewrite this as integral. First I'm going to integrate with respect to x, okay? And x runs from 0 to y, 2y squared sine of xy. And y runs from 0 to 2, okay? I'm going to rewrite the whole thing a little bit nicer, and I'm pulling out the constant 2. So from 0 to 2, to the integral from 0 to y squared sine of xy dx dy. First, I'm evaluating this integral with respect to x. I treat y as a constant, so y squared. Integral of sine of xy is negative cosine of xy over the constant y, evaluated from 0 to y, dy. That's equal to 2. This guy canceled. Integral from 0 to 2, y times, and this negative, pull it outside, negative right here, right, this negative. So I have cosine of y squared, cosine of y squared, times x is equal to y, right? So instead of x, I put y times y is y squared, minus when x is equal to 0, I get cosine of 0, dy. This becomes -2, integral from 0 to 2, y times cosine of y squared. This is just the substitution rule. If you cannot recognize right away that this is sine of y squared over 2, this integral. Cosine of 0 is 1 minus y dy. And you can see how much easier it is if you change the order of integration. So if you put here u is equal to y squared, du is equal to 2y dy, this is -2. You end up with integral of cosine of u. Integral of cosine of u is sine of u, which means sine of y squared. What is it right here? dy over 2 minus y squared over 2 evaluated from 0 to 2. And you're done. This is equal to -2. So here I have to have that. So you have sine of 4 over 2 minus 2 squared is 4 over 2 is 2 minus 0. Why minus 0? Because sine of 0 is 0 and 0 divided by 2 is 0. So finally here we have 2 times 2 is 4. -2 times -2 is 4. Sorry about that. Minus sine of 4. I'm not saying that this is easy, but at least I was able to get to this value in 1, 2, 3, 4, 5 steps, compared to here where I just saw that in the next 5 steps I wouldn't have been able to get to integrating with respect to x. And this is section 15.1 and 15.2, for which I'm going to upload some extra videos, or not videos, one more video line later on. Are there any questions?